Ever wonder how you actually take a drone from a simple mathematical concept on your screen to a realistic, wind-fighting, trajectory tracking machine? Well, that's exactly what we're going to break down today. Welcome to The Explainer. Let's dive right into our game plan. We're taking a basic altitude controller and leveling it up into a robust, real-world system. We'll hit Level 1, building the foundation, Level 2, anticipating the future, Level 3, the physics of tuning, Level 4, facing reality, and finally, the complete UAV journey. Let's get to it. We're going to be synthesizing the incredible 10-chapter learning arc from Dr. Mohin's MATLAB Drone Coding for Beginners Book 2. It's a fantastic resource because it perfectly bridges that notoriously tricky gap between basic MATLAB simulations and practical, real-world control behavior. All right, Level 1, building the foundation. This is all about refactoring code and trajectory tracking. Look, if you've ever built a simulation, you know the pain. One giant, messy script quickly becomes a total nightmare to manage. So, right out of the gate, we're fixing that. We're splitting our code into dedicated, reusable functions, one for simulation, one for PID calculation, and one for plotting. Doing this upfront makes our drone infinitely easier to modify as the logic gets, well, a whole lot more complicated. Now, here is the crucial shift. We're moving from just hovering at a static point, like telling the drone to just stay at 1.5 meters, to continuously chasing a moving target, like a sine wave. It's a much more realistic challenge. Real drones out in the wild don't just pop up and freeze, right? They run dynamic missions with constantly changing reference altitudes. Moving right along to Level 2, anticipating the future, featuring feedforward and velocity tracking. So what actually happens when your drone's target is moving so fast that a basic controller just can't keep up? We level up. We introduce feedforward control. Basically, we're teaching our drone to literally anticipate its next move, instead of just reacting to past mistakes. If we know the trajectory's expected acceleration, we can just apply that thrust in advance. This really highlights the core difference. Feedback is purely reactive. It only kicks in after an error has already happened, so it's always lagging a bit behind. But feedforward is proactive. It anticipates the desired acceleration and adds thrust ahead of time, which drastically smooths out the entire flight path. But here's the thing. A drone's altitude doesn't tell the whole story. Think about it. It might be at the exact correct height, but if it's rocketing upward way too fast, it is absolutely going to overshoot in the next split second. That's why we have to give the drone an awareness of its vertical speed. Now it calculates both position error and velocity error, so it knows not just where it is, but exactly how fast it's getting there. And here is the payoff. By combining position tracking, velocity tracking, and that feed-forward control, our mean absolute tracking error shrinks down to an incredibly tiny 0.0320 meters. That is just 3.2 centimeters of error while actively chasing a moving target. Pretty amazing, right? Okay, let's step up to Level 3, the physics of tuning. This is all about systematic gain design using dynamics. At this point, we really have to stop and ask ourselves, why on earth are we relying on endless trial and error to tune a drone's PID gains? Honestly, guessing parameters by randomly tweaking proportional and derivative values is frustrating, and it's incredibly inefficient. It's time to stop guessing and start using actual physics to tune our controller. Instead of guessing, we use second-order system dynamics. By clearly defining how fast we want the drone to respond, that's our natural frequency, and how smooth the flight should be, our damping ratio, we can mathematically calculate the absolute perfect proportional and derivative gains. We're not hoping for the best anymore, we are literally designing the exact shape of the flight response. Now things get really interesting. Level 4. Facing reality. It's time to tackle actuator saturation and anti-windup. So our drone has this perfectly tuned mathematical brain, but now we have to face the harsh truths of physical hardware. Think of it as a battle between the brain and the muscle. The math, the brain, might demand, say, 20 newtons of thrust to fight off a sudden gust of wind, but the real-world motors on our little drone physically max out at 13 newtons. That bottleneck is what we call actuator saturation. And when those motors max out, the brain gets seriously confused. Because the drone isn't reaching the target height fast enough, the controller just keeps piling on more and more requested thrust. This leads to a highly dangerous problem called integral windup. The integral term essentially remembers all this past error and builds up a massive, physically impossible request. It's easy to see the dangerous consequences here. Without anti-windup protection, the controller demands that impossible thrust, which leads to massive overshoot and these wild, dangerous oscillations as the drone finally tries to recover. The thrust is just desperately bouncing around because the integral term essentially lost its mind while the motors were maxed out. Thankfully, we have a fix for this. By applying a technique known as conditional integration, we basically tell the controller to just pause, stop accumulating error while the motors are fully saturated. Notice how much faster and cleaner the thrust flattens out? This simple logic results in a drastically safer, smoother recovery. Another fantastic approach is using a clamped integrator. This method allows the error to update, but it strictly bounds it between fixed upper and lower limits. It's just another highly effective, realistic method to protect against windup. Both of these strategies are crucial for protecting the drone from its own physical limitations. And that brings us to our final section, the complete UAV journey. Time to put it all together. We've now fully equipped our simulation. Look at everything we've built here. We went from organizing messy code into a sleek, reusable architecture to designing a system that proactively anticipates motion using feedforward acceleration. We added position and velocity feedback for truly realistic motion control. We used physics to systematically self-tune the system, mapped out physical hardware constraints with actuator saturation limits, and intelligently protected the drone using anti-windup algorithms. We literally transformed simple textbook math into realistic UAV control. To quote the book's author, drone control coding is not only about writing MATLAB commands, it is about connecting the code to physical meaning. Dr. Mohin really hits the nail on the head there. The entire goal of this explainer is to bridge that massive gap between abstract equations on a whiteboard and the actual physical forces keeping an aircraft in the sky. Every single line of code has to respect the realities of physics. You now have the complete blueprint to simulate reality, pushing way past the limits of basic feedback loops. So, armed with feed-forward control, systematic tuning, and anti-windup protection, what kind of drone will you simulate next?